All right, so we're going to talk briefly about something in this video called valence bond theory. And this is basically trying to more directly tie quantum mechanics to our structures that we've been drawing. I mentioned that there is a link, and we have been using, valence electrons, this idea of valence electrons, which we're able to get from the shape of the periodic table, and the shape of the periodic table comes from quantum chemistry. But it's been kind of a tenuous connection. And so this theory sort of connects these a little bit more. And so this is a quantum mechanical model, and it shows how electron pairs are shared in a covalent bond. And basically what it says is that a covalent bond is formed by pairing two electrons of opposing spins, and that there's a region of overlap between these two atoms. And without getting into any math, basically stronger bonds have better overlap, okay, between these atoms, the wave functions of the electrons atoms, okay. And so what this theory ends up trying to do is come up with a way to construct orbitals so that you can have effective overlap. And in order to do that, you have to have the proper symmetry. You saw that, for example, for methane, right? We know from VSEPR that that's tetrahedral geometry, and that's true. Experimentally, methane is a tetrahedral, has a tetrahedral shape. You can see this experimentally in different ways. But what valence bond theory is trying to do is then ask a little bit about, okay, how is that bonding now going to have, how are those wave functions going to have shapes that are also tetrahedral? An s orbital is a sphere. A p orbital is a dumbbell. Okay, how do you get a tetrahedral shaped orbital? And so what hybrid orbital theory actually says is that we're going to mix p and s orbitals, or p, s, and d orbitals, and make sp3 orbitals, for example, in the case of tetrahedral. So if you have a tetrahedral geometric steric geometry, you're going to have sp3 orbitals, because you're going to have 4 sites there, right? 4 bonding sites. Tetrahedral has a steric number of 4. So you take 1 s orbital, 3 p orbitals, you mix them together, and you're going to get 4 sp3 orbitals with that type of geometry. Okay. So basically, there's just this table saying, hey, sp, that's 1 and 1, that's steric geometry of 2, linear. sp2, that's 1 and 2, steric geometry 3, trigonal planar. sp3, we just said that, 1 and 3, steric geometry 4, tetrahedral. sp3d, or dsp3, you can write it that way. That's going to take 1 d orbital, 3 p orbitals, 1 s orbital. That's going to get you steric geometry of 5, trigonal bipyramidal, and finally octahedral sp3d 2. That should say 2 there. Okay, d2 sp3 2, d2 sp3. That's going to be 1s, 3 p's, and 2 d's. Okay. Now, I'll give you a little just insider's view to how I feel when I'm teaching all this. It turns out all this is wrong, okay? And yet, chemistry curriculum, and if you take the MCAT or something like this, you'll be asked this. So I want to teach it to you, but it's all wrong. And if you want to know why it's all wrong, you'll have to take an advanced chemistry class, and you won't really learn why it's wrong until graduate school. But it turns out this is an approximation, and there are many experiments that you can do that showed you that sp3 orbitals and all these hybrid orbitals don't exist. And so it turns out to be a model, right? Everything's a model. And this model turns out, in my opinion, to be very bad. And so if I were the designer of chemistry curricula, which I'm not, I would not include this. But, I'm just doing my due diligence for those of you who are taking the MCAT. I might test you a little bit on this on the exam. It's not going to be a huge focus. But you're going to see it in your future chemistry classes. So that's part of the reason I have to go over. All right. So sp2 hybridization. This is going to be 1s orbital, one space s orbital, not the 1s. It could be any s orbital. It could be a 2s, a 3s, a 4s. Okay. And 2 of the p orbitals, and they're going to mix. And you're going to have steric geometry 3 here. So they're going to make things that look like this, these green things. They mix. Okay. So red and blue is going to make these green things. And then together, that's going to set up your 120-degree bonding angle. So another way of showing that is, hey, look at boron trichloride. That's an example molecule that has sp2 hybridization. Take your 2s, your 2p's, you're going to mix them and make 3 sp2s. And you're going to have a certain number of valence electrons, right? There's 3 valence electrons in boron. Those are shown here. And one of these orbitals is going to be unhybridized because you only took 2 of the 2p's, 1 of the 2s's. Now you're going to put them in there, okay? SPs, it's very similar. Now it's only 1s and 1p. That's going to set up to make your 180-degree bonding orientation. And so how this sets up, right, then you're going to have 2p's that are unhybridized if you're talking about like a carbon atom that's using 2p orbitals, okay? So if you look at acetylene, that has this Lewis structure with the triple bond. In the middle, there's 10 valence electrons, so 2, 4, 6, 8, 10. And you're going to have 1 carbon and 2 carbons here. Both of those are going to have 4 valence electrons total because it's in group 4 on the periodic table. 2 of those are going to go in the 2sp orbitals, and 2 of those are going to go in the hybrid orbitals, and then you're going to make a bond. And you're going to make a sigma bond between 2 electrons per bond. That's going to be one of your single bonds. That's called a sigma bond, okay, between your hybrid orbitals. And you're going to make other sigma bonds between the 1 electron that's in each hydrogen, okay? And then you're going to make what's called a pi bond between 2 pi bonds between the unhybridized p orbitals. And that's going to get you a single, double, triple bond, 2 pi bonds and 1 sigma bond, okay? And so how this ends up looking is something like this. Basically, it's just the way that all the orbitals can overlap, that you have the right symmetry. So the p orbitals have symmetry. They get this kind of perpendicular overlap. That's why they're called pi bonds. Pi stands for perpendicular. And S is sigma bond. It's more like straight on bonding happening here. Again, I just want to give you kind of the general idea of this stuff. You don't really have to worry too much about it for this course. But what you will have to do is questions like this, and we'll go over those questions, how to do them. They're very simple on the next video.